let's go to page 310. Today's lesson is lesson 5.3. And this lesson is to use angle bisectors of triangles. So this is very similar to the perpendicular bisector from the previous lesson. So it says, remember that an angle bisector is a ray that divides an angle into two congruent adjacent angles. So here's an example of that. So you have an angle is made out of two rays. An angle bisector is the one that goes through the middle and make two congruent angles. Okay? Remember also that the distance from a point to a line is the length of the perpendicular segment from the point to the line. So the distance from the angle bisector to the side is a perpendicular distance. So if you draw a right angle over here, draw the right perpendicular over here and perpendicular over here. Okay, so that's what this is. So again, this is a distance. Okay, so in diagram, ray PS, so that's the ray, is a bisector of angle QPR. So this is a bisector of PQR. And again, if you see the marking right over here, see this marking shows that these two angles are congruent. Okay? And the distance from S to PQ is SQ. So SQ, and where SQ is perpendicular to PQ. Okay? So again, the distance is a perpendicular distance. Okay? So the couple things to notice is that when you are angle bisector, the two triangles would be congruent. So the distance would be equal. So SQ will equal to SR. Okay, and the angle, this angle and this angle would be congruent. Okay, because the two triangles would be congruent triangles. Okay. Okay, so let's go to the theorem. So theorem 5.5, angle bisector theorem. It says if a point is on the bisector of an angle, so any point on here, so just choose a random point like point D, okay? Then it is equidistant from the two sides of the angle. So again, any point on the angle bisector is equidistant to the side, okay? So this is almost like the perpendicular bisector, except perpendicular bisector is like a straight line, right? So imagine if you have a straight line and you bend into an angle, so you can see the same concept. Okay. So again, for perpendicular bisector, you have a segment right over here, and this goes through the middle. Okay. But instead of cutting the segment right now, you're bending the segment into an angle, and so it cuts through the middle. So it's very similar idea. Okay. So here it says if AD bisect the angle BAC, so cut this into two equal angles, then DB is perpendicular to AB, and also DC is perpendicular to AC. Then DB equal to DC, so DB equal to DC. So here's a key point right over here. Okay, when you're an angle bisector, then any point on the angle bisector is equidistant to the two sides. Okay, so again, so BD is equal, DB is equal to DC, so distance will be equal. Okay, just like before, when you have the perpendicular bisector, okay, if it's straight, right, then it is equidistant to the endpoint. Okay, so same thing. Think of this like your endpoint. Okay, so just like before, you have the converse of the angle bisector theorem. So it says if a point is in the interior of an angle and is equidistant from the side of the angles, then it lies on the angle bisector of the angle. So what it's saying is that if a point, okay, on the inside and is equal distance to the two sides, then it is on the angle bisector. Okay. So again, if a point on the angle bisector, then it's equal distance to two sides, and converse. Okay, if a point is equal distance to the two sides, then it is on the angle bisector. Okay, so now let's go over the example of how to use the angle bisector theorem. So it says find the measure of angle GFJ. So you're looking for GFJ. You're looking for this angle. Well, if you notice that this length is 7, okay? So this is the length of 7, and this is the length of 7. So this is equal distance to the two sides. That means this is the angle bisector. And if this is the angle bisector, then two angles would be congruent. So if this is 42, then this would be 42. Okay, so again, so the answer is 42. Okay, and again, notice that two triangles would be congruent. Okay, so two triangles would be congruent. Okay, now let's go to page 311. Solving a real world problem. Okay, it says a soccer goalie's position relative to the ball and goalpost form congruent angles as shown. Okay, and where the goalie have to move further to block a shot toward the right goalpost R or the left goalpost L. So if he's standing right in the middle, okay, facing the kicker, okay, does he have more further to go on this side or this side? Well, the answer is same, okay, because again, using the principle of angle bisector, okay, this will equal distance to either side. Okay, so if he stay in the middle, then he will have the same distance to cover on either side. Okay, let's go to example 3. It says use algebra to solve problem. Okay, so for what value of x, okay, lies on the bisector of angle A. So it says if this point P is on the angle bisector, what would be value of x? Okay, again, if the point P is on the angle bisector, then that means the distance will be equal. So you set them to equal to each other, right? So you got x plus 3, this distance over here, the distance of BP, and equal to the distance of CP, right? Set it equal to each other. And then you minus x on both sides, and you plus 1 on both sides, so you get x equal to 4. Okay, so x equal to 4. Okay. Let's go to page 312, theorem 5.7, concurrency of angle bisector of a triangle. Okay. So when you have 3 angle bisector, they're going to meet in a point. Okay, so that's reason why it says the angle bisectors of a triangle intersect at a point that is equidistant from the side of the triangle. So the angle bisector from here, angle bisector, they're going to meet in one point, and this point will equal distance to the side, to the side, to the side. Okay, so it says if AP, BP, and CP are angle bisector of triangle ABC, then PD, okay, so PD equal to PE equal to PF. Okay, and because of that, okay, since the angle bisector, okay, they are equidistant to the side, so that means that this will become radius of circle, because this distance is all same. That becomes the radius of the circle that inside, because this distance is radius, this distance is radius, this distance is radius. Okay, so from here the angle bisectors meet at a point called the incenter. And incenter, because this is the center of the inscribed circle. See, in center, so it's a center of the inscribed circle. Okay, whereas on the perpendicular bisector, this is equidistant to the corner, to the vertex, So this has become the radius of the circle on the outside. Okay, so make sure you kind of be aware of all the significance of those bisectors. Okay. So let's go back to this over here. So it says the point of concurrency of the 3 angle bisectors of a triangle called the incenter of the triangle. The incenter always lies inside the triangle, because the incenter P is equidistant from the 3 sides of a triangle. A circle drawn use P as a center, okay, over here, and the distance to one side as a radius will just touch the other 2 sides. The circle is said to be inscribed within the triangle. Okay, so that's what we just talked about. Okay, example 4. Use a concurrency of the angle bisector. In the diagram, N is an incenter, means the center of the inscribed circle of a triangle ABC. Find ND. Okay, well, notice that AN is 20 and AF is 16. So if you use a Pythagorean theorem, okay, so you got A squared plus B squared equal to C squared. Okay, so remember, C is always a hypotenuse. Okay, so AN is a hypotenuse. So you got 20 squared equal to NF squared plus 16 squared. So you can A squared plus B squared equal to C squared. So make sure you know these. Okay? Then after that, you work it out. 20 squared is 400, 16 squared is 256. Okay? Then you minus 256 on both sides, so you get 144. Okay? So 144 equal to NF squared, so you take the square root, so NF equal to 12. So once you find NF equal to 12, this is your radius of the ink circle, okay, inscribed circle. So if NF is 12, then ND will equal to 12, NE equal to 12, okay, and that's your answer, okay. So again, NF equal to ND, so ND equal to 12.